last class we had finished off with some of the properties of the MM1Q, right, the performance analysis based on deriving the steady state probabilities. So let us look at some other variants of this MM1, but before that we look at a generalized version of a birth death process, right. So this is a generalized okay. So the characterization is that we have again a set of finite or countable set of states, and the transition rate from state 0, right, is given by lambda 0, this is mu 1 and so on, okay. So the arrival and departure rates are state dependent. In the previous example that we saw, lambda was equal to mu, right, all the lambdas were the same, and sorry, not lambda equal to, all the lambdas were the same and equal to lambda, and all the departure rates were the same and equal to, but because this particular formulation appears often, right, let us try to derive one common expression. From that we can always derive the subsequent for all the different systems that we will look at. Okay. So we will derive this, but the basic thing that we want to prove is the steady state probability of being in state n, which is given by Pn, so if you look at some state n, right, so what comes in is at the rate lambda n minus 1, and what you leave it with the rate mu n, right. So this is simply the product of all the arrival rates from lambda naught to lambda 1, so if you can see that, okay. What I move here you probably cannot see, okay, that is what I am trying to, so just all the, right, lambda 0 into lambda 1 up to lambda n minus 1 divided by the product of all the rates, the departure rates, mu 1 or mu 2 to mu n, that is about it, times P naught, where n goes from 1 2 to infinity. So P naught is the probability of being in state 0, so everything is expressed as a probability of, as a multiple of P naught, and because all the Pi sum, all the Pn sum to 1, we can always solve for the equation that we want, okay. So this is an easier way of remembering, right, what we did the last time. So it is simply product of all the I guess birth rates divided by the product of all the death rates up to the state n, that is it. Make sense? So that is what we will try to prove, and we will try to prove it slightly differently this time. So last time we wanted to see how we wanted to see this treated as a discrete process, right, as a discrete time process. So we will try to look at this as a discrete time process, okay. Okay. So suppose that at so n of t, right, is the variable that I am trying to, I am interested in. N of t is the number of customers in the system, right, at time t. And so what we need to look at is, so assume that we are looking at increments of delta t, so looking at the system in terms of t, t plus delta t, t plus 2 delta t and so on, right, or 0 delta t, 2 delta t and so on. So the basic time increment is delta t, okay.
We are making a continuous process into discrete.
Yeah, we are trying, yeah, the process is still continuous, but what if we look at model that as a, look at the probabilities in terms of discrete time intervals, okay. So this is what we would try to find out. So the probability so given that at time t, right, I was in state j, okay, what is the probability that at time t plus delta t I will be in state j plus 1. Remember I can only go from j to j plus 1 or to j minus 1, right, and delta t is so small that only one of those two is possible, or I could of course stay in state j itself, right. For just looking at what is the probability of that going to state j plus 1, so what is the probability going to be? So this is the probability of exactly one arrival, in delta t, right. And what is that derived to be? If you go back to our lambda j to delta t.
We can have two departures and one. I mean,
You are assuming that there is at most one arrival or one departure, that delta t is so small. Okay. So that is dependent on the birth rate at state j, and likewise the probability that I go to j minus 1 is the probability of I am using the terms arrival and birth interchangeably. So this is again mu j into delta t.
Probability of one arrival in delta t into probability of only no departure in delta.
No, only one of those two is presumably is going to take place, right? Okay, yeah.
So this is going on.
Okay,
So you can divide.
okay.
We need to put another condition that in delta t.
That there is no departure. Okay, now let me see.
but if you assume
Okay.
only one can take place,
Let's see how to get the intuition right. So in delta t you have these two different processes, right, and what seems intuitive seems hard to explain. Okay, okay, I'll come back on that, right, as to why we don't need to quantify that, right. So this times the fact that there is no departure from the system, right. Okay. And the probability of n of t plus delta t equals j, given that okay. So that is simply the probability of no departure, no arrival in this small time interval. So the one explanation is that delta t is so small that you cannot have even not even two arrivals, even two events cannot take place, only one of the two can take place, right. So either an arrival or a departure.
probability of such event
I am sorry,
probability of such event will include delta square,
delta, which will go to 0, right. Okay, so this is the probability of staying in the same state. Delta t is very small, this will be the probably the high, right, fairly large, closer to 1 if depending on the product of these two. Okay, so now let P naught of t, okay, or P. This is the probability of being in state j at time t. Okay, so now we can define the probability of say P naught at time t plus delta t. Okay, so what is the steady state, or at least an probability of being in at some, not just steady state, just look at t, and at time t plus delta t, right, I will be in state P naught when two cases happen. This is where your question will come in. So either I was in state t or state 0 at time t, okay, into no departure from that state, that is 1 minus lambda 0, right, because there is no mu there, and then P1 of t, what is the probability that I am in state P1 but there is a departure from that state. Okay, so P naught no departures or no births, or P1 and there being exactly one departure or one death, right. So this is the probability that I will stay in state t. Okay, right. So 0, I was in state 0 and therefore I stayed in state 0. I was in state 1, I moved to state 1 with this probability. That is what we derived in the previous. And likewise I will write the same thing for P1 also. So P1 onwards it is slightly different, right. So P1 t plus delta t is, so first from P naught I will move to P1 with lambda delta, right, lambda 0 delta t into P naught of t, plus I will stay in and then I would have been in state 2. So therefore the probability of coming from state 2 is this. Okay. Questions so far have been sort of routinely deriving.
Probability of being in steady state will be different from this.
When t goes to infinity, that will be the steady state. That is what we will try to derive. This is the instantaneous probability of being in state j at or at time t plus delta t. Okay. Okay. So now let us derive P naught so what is that equal to? So okay, just tell me, you have the expressions in front of you, right? Sorry, mu1 into
P1 of t
then
minus P naught of t lambda naught.
to lambda t, right. So this is basically, so I will let you work it out. So when this limit goes to infinity, this goes to infinity, what do you get? 7. Right. Oh, sorry, I am jumping there. Other definition as t goes to infinity, right. So this is one, right. So this is your definition of the derivative. So then so assume that it is as okay, as t goes to infinity, right, approaches the steady state probability P naught, right, or in general so as steady state approaches, your P naught of t approaches the steady state probability P naught, right. So what happens as t goes to infinity, the differential of all the pj's go to 0, right. So therefore it is all your and so plugging in here we will come back to our famous, right. So the last time we derived this, we looked at that Q matrix and said we can arrive at the same thing. This time we are going back to the basic definitions, right, of the change with respect to time. So likewise you can derive the same thing for Pj of, so that was a special case, right, for P0 and P1, but when you go to other Pj's then the expression is slightly different. So this is lambda j minus 1 delta t Pj minus 1 of t plus 1 minus lambda j minus. Right. So these are fairly easy to remember. So I can now again apply the same thing, right. So I can derive Pj of t and apply set that is 0. So what will that be? So finally what is the balance equation we will get? I am not doing that, I will ask you to do that, right. So do the same thing we did before. So limit equals something that equals 0. So dot 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 dot. So therefore what do we get? Lambda j minus 1 Pj minus 1 plus mu j plus 1 P equals again just remember this is balance equations, right. You are coming in from the previous state with rate lambda, coming from the next state with rate mu, and that equals to the probability of staying in the same state. Did I get that correct? Yeah. So since we did the relationship between P0 and P1, now is this okay? You are able to get this, right? So substitute j equals 1, right? Then what do you get? Because we have P1 P0 relation, we need P1 P2, right? We did this the last time, but we're going to be the same thing. So it's going to be lambda naught P0. Yeah, we did the same thing with M1, it was lambda and mu. So once we get here, it's the same thing, but just want to show another way of getting to the same thing, right? So this is which is basically lambda 1 P1 plus mu 1 P1, but we also know that lambda 1 or mu 1 P1 is the same as right. So what do we get at the end? Mu 2 P2 equals lambda 1 P1. Agreed? So these two cancel out. So proceeding likewise, we come back to our Pn, which is, if you want, that's all. So that is what we wanted to discuss. We only had it as lambda 1, lambda 0, lambda 1, but be consistent with the equations on this page, I am just reverting. Okay, so that is our basic derivation for any lambda mu for a birth death process. So to give you any set of rates, you should be able to just apply this and derive this and get the answer right. You do not have to go back to basics and derive each time, right? Questions?
So what we say is once we have reached a steady state, then there is going to be no addition of number. If you see it in this equation,
This is the steady state probability of being in a particular state, yes.
every time we see increase the n, the lambda mu also gets added up.
You tell me increase and
Like suppose we have to take out for P3, then we have like lambda 3 over mu 2 into
okay.
lambda 2. Then we go for P4, then again one more variable will come, lambda 4.
That's okay. But that's a formula for Pn in general. That depends upon the birth and death rates of all the previous states. That's what you're saying, right? Yeah. So.
Once we have reached steady state, then
Okay. So you are saying that at steady state you will just reach one state and stay there, right? So but what's happening is this is a process that's going back and forth. that is the purpose of trying to work out your the programming assignment 1, which I presume that all of you have seen, right, where you are trying to do essentially a Monte Carlo simulation of the states that you are moving, right. So what is happening, there is a probability of going from one state to another state, right. Assume that it is like a random walk where you start in one point and you go back and forth between the different states, but what you want is on long term what is the probability of being in one state. You are not going to be stuck in a state, right, that means that will be an absorbing state. You never have in this case there is no absorbing state, then there is a the probability of being in these different states what you are trying to compute. Probability of say point 1 you will be in state 0, point 2 will be in state 1 and so on, right. That does not mean your system is a dynamic system, right, in every time instant you are changing states, but if you keep running this for a million time units or 2 million time units, then you look at the actual distribution, right. What is, so if you run it for a million time units, right, and that is what you will count, and then try to measure what fraction of time was I in state I, that is your steady state probability, right. So you run it for a million times and then see how long was I in, how many time instants was I there in state I, that is your steady state probability, right, not that you will get stuck in a state, right. So you are ultimately you will converge to that if that limit exists for this particular system that you are looking at.
So when you say like V is equal to Vp,
Mhm.
so that also is the same?
That same thing, yes. Vp equals V means that I started with some state V with some probability distribution, right. So if you are saying that this is the current distribution of my different states, right, I have a single step, I know the transition, this is your transition probability matrix, right. So whatever be this, I will end up in being the steady state probabilities of being in the different states does not change after just one more transition. That's what it means, right. You will be in different states at different points in time, but the long term distribution of the probabilities is what you are trying to calculate. Which one should we do first, MMM or MMB1? MMM, okay, all right. We have both coming up, so one way or the other you are going to see both, it's just a matter of when. Okay, MMM. So this is your multi-server system. Okay, so the same Poisson arrival, same exponential departure service time, but there are M servers in the system. So this is where we started off last time, right? And you are trying to see what is the intuition by saying that this is these are departure, the service rate, the rate at which I leave a state is proportional to the number of active servers, right? So there is a single common queue, okay. So the representation for this is there is one queue to which all the packets arrive, and then there are a set of parallel servers. And each server is operating at rate 1 over mu, or with service time 1 over mu and rate mu, and the arrival is lambda, right. So only one common arrival. So compared to, before we do the analysis, right, compare this to a single MM1, single server MM1 queue, right, to multi-server MM1 queue. Both of them have the same capacity, right, mu packets per second or customers per second. Of the E of t, right, or the E of r, response time, number of customers and so on, right, which will be less in this system? Response time will be less in this system. How about the waiting time? Waiting time will be less because you have multiple servers. Okay. So when we'll compare this to a system where I have capacity of mu rather, right. So I have M servers in parallel with total capacity M over mu, but we look at a system which has single server with capacity M mu, and then we will try to see which one is better, right. That will be the next analysis. So for now let us just derive this routinely, then we will start applying some numbers to see the difference. and so on, right. So you return with the rate n mu for all states less than m, and greater than or equal to m, it is m mu. So we will define this utilization factor. So utilization is the ratio of the total arrivals to the total capacity of the system, right. So what is the total arrivals? That is at lambda packets per second. Total system capacity is m into mu, right. So we will use this. So the rho is defined the same way as before. Where m equals 1, then the definition does not change, right. So rho equals lambda by m mu. So we will use this rho as we go along. So now that we have derived that generic birth death process, right, I simply have to blindly apply that here, right. So there will be two cases, right. For all cases of for Pn, I am trying to derive Pn, the steady state probability less than or equal to m, I will have one expression, greater than m, I will have a different expression, right. So if you want to again do this sort of one step at a time, so P1 is lambda my rho into P naught. Right. So what is P m minus 1? Lambda by, so there are m minus 1 terms here, right, and then you have m minus 1 factorial mu m minus 1 P naught, right. So it is simply mu into all the way up to m minus 1 mu, then P m is again just I am just writing this one by one so that we can come up with the generalized expression, right, that makes sense. So how do we generalize that? M factorial mu plus 1 extra m is there, right. So you can generally make this m plus I if you want is lambda m plus I m factorial mu m plus I of I. Okay, now for P naught is always present, right. So can you simplify this to something more rememberable, something easier to remember? So try to use lambda lambda equals or rho equals, right. So if you use this definition, then what does my P naught Pn become for n less than m? So lambda by mu is m rho. Yeah.
So I did not get why that m is
Where? This one. That's because you have mu into m minus 1 mu and so on. So it is 1 all the way through to m, then becomes m factorial, right?
So it should become m plus 1. No, the last m.
This one, p m plus I. So this is state I. So up to m you have 1, 2, 3 up to m. Then you have out of that simply m for the last I states, right? Your multiplicative terms are 1, 2, 3 all the way up to m, and then it's m repeating, right, I times. So how do you simply simplify that? So therefore we can say lambda by mu is equal to m rho, right? So we'll talk of m rho, everything in m rho. And then for n greater than or equal to m, so what is the corresponding expression for n greater than or equal to m?
M power n, rho power n by n.
Okay, m rho, we will use m rho p naught divided by, there is m factorial, and then there is mi, ni is basically, since we used simply n minus m, right. So therefore P naught is, so basically we can derive the again steady state probabilities as before. So this is now simply we'll use so this corresponds to P naught, this corresponds to all the 1 to m minus 1 states, and this is m rho to the power n by n factorial and then of course one big inverse. Okay. So can we simplify this any further? Second term can be or cannot be? If rho is less than 1. Second term? Third term, yeah. Okay. Okay, go ahead and simplify the third term and tell me what the answer is. So we want to simplify this fellow, right? We will separate this out, m divided by m factorial m to the n minus m, n going from so what are the things that are unrelated to, oh no, I got this all wrong, right? You have to be careful. Isn't that an n there? Yeah. Okay. So what comes out of the summation? I need you to work it out, and m factorial comes out. Then what else? What does this become? I know you got it. So what does this simplify to? Rho power m by 1 minus rho 1 by 1 minus. Now you'll have to extract the, you can have to replace n by m plus I, right, and then I goes to 0 to infinity. So you have to get back to 0 to infinity. So this is basically m rho to the m divided by so to that get that summation, it is 1 over 1 minus rho, we need the rho less than 1, right, only at that point we can simplify. Make sense? If you didn't get, you have to go back and complete the derivation if you are kind of vague on that, right. If you want, I will simply say so replace n by m plus I, then rho m comes out, then you only have rho I, and the indexes go to I equals 0 to infinity. So I want, okay, so that's one simplification, right. So therefore P naught is I have to be very careful. Did I put n equals 0 in the previous term? No, not okay. And if rho is greater or equal to 1, this also becomes unstable, right, because that summation and the large right side keeps going to infinity, and then P0 goes to 0, then everything goes to 0, right. So therefore this condition for the Q to be stable is again that the rho should be less than 1. Okay, so now we have this. Now we need to find out the expected number of customers, E of n, E of nq, E of t, all that stuff, right. So now different queuing systems, it is easier to find different metrics easily, right. So in the case of MM1, the E of r was easy to remember, just 1 over mu minus lambda, but in this case we will find that something else is easy to remember, right. What is E of nq in the case of MM1? E of nq was rho squared by 1 minus rho, okay. That rho squared by 1 minus rho is what we will be actually trying to derive something equivalent here. Only thing is that rho squared will be split into two parts. That rho has two meanings, one is the utilization, and it also means the probability of an arriving packet having to wait in the queue. So rho is the probability of queuing, right, PQ as it is called, which means that the server is busy, right, in that case, in the case of MM1. So likewise we will derive a parameter called probability of queuing here, or metric called probability of queuing, that will use the same way. So instead of rho squared by 1 minus rho, it will be rho into probability of queuing divided by 1 minus rho, that is what E of nq will be for an MM system, right. So to derive that, we need to derive the probability of queuing. So what is the probability an arriving packet will be queued? And the book has this annoyingly looking variable. I could have preferred PQ, but this is what it uses, and yeah, I am not going to spell that, I will simply call it as PQ. And yeah, I know, but now that we are, that time this book was a side reference, now it is a main book, so we will stick with this book. Okay, this is PQ. So let us derive this now. So what is the probability of queuing in an MM system? When will a packet be queued? When all the servers are busy, right. So that means that, how do you describe that? So this is the probability that all M servers are busy. Or if you go to a bank, the server is pretending to be busy, right. So they will always be looking down and trying to do something on the system because they do not want to handle your request. Okay, so what is that in probabilistic terms here in terms of our steady state probabilities? The probability of system being in state greater than equal to m, right? So Pn is the probability of being in state m. So whenever the number of customers in the system is more than or equal to m, that means all the m servers are busy, right? And therefore you end up being queued. If there are m customers in the system already, you are going to get queued. If there are m plus 5 customers, you are going to get queued, right? So that's why your probability of queuing is simply that.
We are looking at a probability of when a packet arrives, that will be queued.
Yeah.
So it can
Arrive.
arrive at any PM to PM.
Yeah, you can arrive at whatever be the current state of the system, an arriving packet will get queued. And this, by the way, we just now derived, right? So this is simply even if all servers are busy, you have to wait. M servers, I mean, so you are coming to the system state is m, right? So if you come to the system at that time, you're going to be queued. If you are coming to the system state is m minus 1, you are the mth customer. Therefore, system is not, there is one server to serve you. The m plus 1th customer is arriving to the system because you are starting from state 0, right? So state 0, you go to state 1. So when there are already m customers in the system, this plus 1 is always going to bother us, but for now we just take that. And you can question all this, you can verify all this by when we do our next part of the course, which will be the simulation, right? You can verify this in discrete event simulation that this indeed is actually, for MM1 it's close to what we see in theory, right? Only we are going to other distributions, it's hard to verify, it may not be a close match, okay? So this is my probability of queuing. So this is one of Erlang's formula called Erlang C formula, don't ask me why, but Erlang was some guy who was in the early 19th century or 20th century who was working on designing these telephone networks, right? They were just about 30 years old, and he wanted to make sure that the customers, right, did not face a lot of block calls. In the olden days, you simply called up the exchange and said, give me a connection too, and then put the phone on, they'll call you back, right? And there's direct dial is not there. Even 20 years ago, direct dial was not. I'll book a trunk call. That's what we used to do, right? Because you had to wait for. So you wanted to reduce the waiting time. You also wanted to reduce the time that the customers would get dropped, right? So in this case, you are getting queued. When you look at the generalized MMM system, then the customers get dropped, and that is your next Erlang formula, right? What's the probability that, for example, in a cell phone system, right, your cellular network, you try to make a call, all the channels are busy, then you end up getting dropped calls, right? Okay, so now let us try to derive, as I said, E of NQ is easy to derive in this case, and then we can derive everything else from that. So what is the number of customers queued, expected number of customers queued in the system? Again, how do you pose that using the steady state probabilities? Now you look at each state. Okay, look at every state. Where is queuing taking place? From states m plus 1 onwards, right? The m, there is no queue, there are 0 customers, but we can still, so m plus 1, m plus 2 and so on, the number of customers queued is 1, 2, 3 and so on, right? So you will have queuing only when you go from m plus 1 to infinity. The number of customers queued is n minus m, right, times Pn. That's all. So we will again use the definition for Pn. So what is Pn? Because it is greater than n plus 1, we have to use this formula, right, rho m by m factorial. In state n plus 1, right, there are m customers being served, right, and therefore one guy is waiting. So the number of waiting customers is 1. This nq is the number of waiting customers, right. So when you are in state m plus I, there are I customers waiting. N minus m is the number of, yes, n minus m is the number of customers waiting. So to derive E of n we did p n into Pn, but now it is slightly different, right. If this were an MM1 queue, would have said state 2 to infinity, it is always n minus 1, right, whatever be that. Yeah, this is expectation of NQ, yes. Probability of probability of queuing into E of n.
Total number of customers which have been queued, right? N minus n.
Number of customers that are queued is
So this is, you are looking at every state. This is expect. So at every state you are looking at the number of customers that are waiting for service. Okay, and the other way that you are saying is, I have not tried that. You can try that in the tutorial, but so you are looking at the delta, that whatever that the PQ that we derived. Okay, so PQ is the probability that a customer will arrive to a queue. Okay, that into the total no number of waiting customers. That's what we are trying to derive. We are trying to derive that. That's n minus 1, right? You are doing that. So you are saying, okay, the expected value of arriving to a queue that is already full is that the PQ value that we derived last time. So that into, that is simply the probability, but we need the number of customers actually in the queue at a given point in time, right, or the expected number or average over all the instance of time. Okay, that alternate derivation we will definitely look at, but for now if we can proceed with this, I will have at least one result. Again I have massaged the definition so that we get this rho m factor out, right. We said m to the m and then rho to the n it was, right. So I took out the rho m outside. If you go back to the definition, right. So replace n by m plus I. I don't know how you do your reductions, but usually I try to do it this way. So replace n by m plus I, then change all your variables, right. So what do we get? So when n, so n minus 1 will become I, right. So I into rho to the I, and this index will now go from 1. When n is m plus 1, then I equals 1, right. And this is something that we have seen before, you know. And here this again should be familiar as you see many of these summations, you know that there is some pattern that we see here, right, because you know the geometric is I rho to the I minus 1, we have done those kind of right when we did the summations before. So this is better if you write this as I minus 1. So I am going to pull out the one row here. So then I have one nice expression. So we know that you can derive or differentiate, right? Do all of you know what I am talking about? Getting the derivation done, right? The differentiation done. Okay. If not, okay. So this is now basically P naught so what is this equal to? 1 over 1 minus rho squared. No funny business there, right? Because sometimes these indexes going from 1 and 0 make some difference. Okay. Right, this we know, this is your sigma rho y, and this is our okay, there I put it in notes. So what does this now simplify to? So this m rho m rho, all that business should look kind of familiar, right? So m rho m by m factorial p naught 1 minus rho, all that we saw in our PQ, right? So there is an extra factor rho, so rho is taken out, my probability of queuing comes here divided by another 1 minus rho, right? This 1 minus rho squared, 1 minus rho goes after that PQ, other one stays here. So that is why rho squared by 1 minus rho, so it looks familiar, right? In the case of MM1, that this probability of queuing is simply rho, the utilization itself, but here it is slightly different, not the utilization amount, a little bit more complex. Okay, so now I get E of NQ, then everything else is easily derivable, right? I know what my E of NQ is, I can find out E of W, then I can find E of R, then I can find E of N, everything. Once I get this expression I can simply derive, I can also go back and derive E of N if I want to, right, like crazy. So I can also derive like N into Pn, right. This is also one way to derive that from scratch. So we can continue that, but that will be E of NQ plus M rho, that I am not going to derive, okay, because one thing is enough, but we know that E of W is E of NQ by lambda . So what is E of R? Waiting time plus service time. What is service time? MMM. What is average service time? MMM. Average service time, that depends upon the server's capacity, which is mu. So average service time is still the same, 1 by mu, whether it is single server or multiple servers. Once you get to the server, you are going to be serviced, right, based on the server's capacity. And then my E of N is simply then if you go to the table on 31.2 you get more detailed expressions for the variance of number of jobs in the system and variance of the number of jobs in the queue and the CDF of the response type, CDF of the waiting time, all those things are available. So the one thing that we do not derive but we just notice is that in case of a single MM1 system the CDF of the response time is also, the response time is basically exponential, whereas in the case of MMM the queuing time is exponential, right, not the response time is different. Yeah. Those things are there. I think those who are really interested should kind of go through those and as a pastime try to derive those or look at some old queuing theory books that just go through these in a lot more detail. For now we are looking at the first order parameters only, right, not much of second order.